In the beginning, there was nothing. No stars, no galaxies, no matter, no light, no space, no time. The vast emptiness we call the universe did not exist. And then, in a fraction of a second, everything changed. From a point smaller than an atom, the universe was born. A singularity containing all energy, all matter, and the very fabric of space and time itself, exploded outward in what we now call the Big Bang. The Big Bang is not just the story of where the universe came from. It is the story of everything, of galaxies and stars, of life and consciousness, of you and me. To understand the origins of time and space is to ask the ultimate questions. How did it all begin? Why does anything exist at all? For centuries, humanity has looked up at the night sky, wondering where it all came from. Ancient civilizations crafted myths and stories of gods creating the heavens, of cosmic eggs hatching existence, of endless cycles of death and rebirth. These were humanity's first attempts to explain the mystery of beginnings. But science, with its relentless curiosity, asked a different question. What if the universe has a physical origin? What if, like a story, it has a first chapter? To answer that, we must travel back, not millions, not billions, but nearly 14 billion years, to the very first moment of time. The Big Bang is often misunderstood. People imagine it as an explosion in empty space. But it wasn't an explosion in space. It was an explosion of space itself. Space, time, matter, and energy all began together. The Big Bang did not happen in one spot of the universe. It happened everywhere at once. Think of the universe like the surface of a balloon. As the balloon expands, every point moves away from every other point. There is no center, no edge. The expansion is everywhere. And so it was with the universe itself, a sudden, furious swelling of reality. Just a trillionth of a second, the universe grew at an unimaginable rate. This event, known as cosmic inflation, expanded the universe faster than the speed of light. What was once smaller than a subatomic particle stretched into something vast enough to become a cosmos. In that instant, energy transformed into particles, quarks, electrons, neutrinos, the building blocks of matter. Forces like gravity and electromagnetism came into existence. The universe was a seething cauldron of raw creation, unimaginably hot, unimaginably dense, a place where the laws of physics themselves were being written. And from this storm of chaos, a universe began to take shape. In the first few seconds after the Big Bang, the universe was too hot, too dense, for anything familiar to exist. Instead, reality was a soup of fundamental particles, quarks, gluons, electrons, dancing in chaos. Matter and antimatter formed in pairs, annihilating one another in bursts of energy. For every billion particles, nearly all were destroyed. But for reasons still not fully understood, a tiny imbalance remained, a sliver of matter that escaped destruction. That sliver would become everything. As the universe cooled, quarks locked together to form protons and neutrons. In the next 3 minutes, an era known as primordial nucleosynthesis, these protons and neutrons began to fuse. Just as stars fuse atoms in their cores today, the newborn universe forged its first elements. Not carbon, not oxygen, not iron, but the simplest ones. Hydrogen, helium, and traces of lithium, the basic ingredients of all future stars. For hundreds of thousands of years, the universe remained shrouded in a blinding fog. Photons, particles of light, could not travel freely. Every attempt to move forward was blocked by electrons and protons colliding in an endless haze. Space itself was filled with light, but it could not escape. The universe, in these early moments, was like the heart of a star, hot, opaque, impenetrable. Imagine trying to look through the densest cloud where every particle of light scatters back at you. That was the early universe. No stars shone, no galaxies gleamed. Only a vast, glowing plasma stretching in every direction. But time is the great sculptor. As the universe expanded, it cooled. After about 380,000 years, temperatures finally fell low enough for protons and electrons to combine, forming stable hydrogen atoms. With this union, the fog lifted. For the first time, photons, the messengers of light, were free to travel across space. The universe, once opaque, became transparent. This was the moment of recombination, the first dawn of light, and the ancient glow from this era has never vanished. It still surrounds us, filling the universe like a faint afterglow of creation itself. Astronomers call it the cosmic microwave background radiation, the oldest light we can see, a perfect echo of the Big Bang. In the 20th century, astronomers made a stunning discovery. This afterglow, this faint microwave radiation, could actually be detected. It is the universe's baby picture, a snapshot of space as it was nearly 14 billion years ago. Patterns within this light reveal the seeds of structure, tiny ripples in density that would one day grow into galaxies, stars, and planets. In the randomness of the early universe lay the blueprint for everything to come. Without these ripples, these imperfections, the universe would be an endless sea of gas. No stars, no planets, no life. Perfection, in this case, would have meant emptiness. The universe had cleared its fog. Light traveled freely, hydrogen and helium filled the void. But the cosmos was still young, still dark. The stage was set for the next great transformation, the birth of the first stars. After the fog of the early universe lifted, space was vast and dark. For hundreds of millions of years, no stars shone, no galaxies glimmered. It was an age astronomers call the cosmic dark ages. The universe was filled with hydrogen and helium, silent and invisible. But hidden within this darkness, forces were already at work. Gravity, the sculptor of the cosmos, was pulling matter together. Tiny ripples of density in the early universe, captured in the cosmic microwave background, began to grow. Regions with just slightly more matter pulled in more gas, their gravity strengthening over time. Slowly, the universe's first great structures were taking shape. In these dense pockets, hydrogen atoms collided, compressing tighter and tighter under their own weight. As the pressure rose, so did the temperature. At millions of degrees, something extraordinary happened. Hydrogen atoms fused together, releasing energy in the form of light. The first stars were born. These were not stars like our sun. They were giants, tens or even hundreds of times more massive. Their lives were short but spectacular. They burned with ferocious brilliance, flooding the cosmos with light, ending the dark ages forever. For the first time, the universe sparkled with stars. Their intense radiation ripped apart hydrogen atoms, reionizing the universe and allowing light to travel even more freely. This era known as cosmic reionization, was the turning point. The universe was no longer a cold, dark expanse, but a place filled with light and structure. And when these massive stars reached the end of their lives, they exploded in cataclysmic supernovae. These explosions forged the first heavy elements: carbon, oxygen, iron, the essential ingredients of life. Scattered across space, these elements enriched the gas clouds, preparing the universe for new generations of stars and planets. Stars are rarely alone. Under gravity's pull, stars gathered into vast families, galaxies. Within 1 billion years after the Big Bang, the first galaxies had formed. They were smaller and more chaotic than the grand spirals we see today, but they were the first great cities of stars, blazing beacons in the young universe. Some galaxies collided and merged, growing larger and more complex. Others remained small and faint. These early galaxies laid the foundations for the cosmic architecture we see now: majestic spirals like the Milky Way, and colossal ellipticals containing trillions of stars. With the birth of stars and galaxies, the universe had transformed from darkness into light, from simplicity into complexity, from chaos into structure. The stage was now set for the long cosmic story that would eventually lead to solar systems, planets, and life itself. Among the countless galaxies that emerged in the young universe, one would eventually become our home. A spiral galaxy that, billions of years later, would cradle a small star called the Sun, and a planet rich with oceans and life. Its name is the Milky Way. The Milky Way's story begins more than 13 billion years ago. At first, it was not the majestic spiral we see today, but a gathering of smaller protogalaxies, clouds of stars, and gas pulled together by gravity. These fragments collided, merged, and grew, gradually forming a larger structure. Every collision was violent. Stars were flung into new orbits. Gas clouds were compressed, triggering bursts of star formation. Piece by piece, the Milky Way took shape, forged in cosmic chaos. Over billions of years, the Milky Way evolved into a grand spiral galaxy. Its flat, rotating disk stretched outward, with elegant arms curving like cosmic rivers of light. Within these arms, waves of star formation lit up the galaxy, painting it with clusters, nebulae, and dazzling stellar nurseries. These spiral arms were not fixed structures, but patterns, like ripples in water, where gas and dust crowded together, igniting the birth of new stars. Some stars burned hot and bright, living short, dramatic lives. Others, smaller and steadier, endured for billions of years, quietly shaping the galaxy's future. At the center of the Milky Way lies a mystery: a supermassive black hole, 4 million times the mass of the Sun, known as Sagittarius, a star. Invisible to the eye, it exerts a powerful gravitational influence, binding the galaxy together. Stars whirl around it at incredible speeds, proof of the darkness that dwells at the heart of our home. Black holes like this are not destroyers of galaxies, but anchors. Their immense pull helps shape the motions of billions of stars, keeping order within the swirling chaos. The Milky Way is not alone. It belongs to a small family of galaxies known as the Local Group, alongside the Andromeda Galaxy and dozens of smaller companions. Andromeda, our nearest large neighbor, is on a collision course with the Milky Way. In 4 billion years, the two spirals will merge, forming an entirely new galaxy. This cosmic dance reminds us that galaxies are not eternal monuments, but living structures, constantly changing, colliding, and reshaping the universe. Our galaxy is but one among hundreds of billions. Yet it is here, within this spiral of stars, that the stage would be set for the rise of planets, of life, and of consciousness itself. Within the grand spiral of the Milky Way, about 4.6 billion years ago, a new story began. A vast cloud of hydrogen, helium, and heavier elements, remnants of earlier stars, drifted quietly in the Orion arm of our galaxy. Then, something disturbed it. Perhaps a nearby supernova, its shockwave rippling outward. Whatever the cause, the cloud began to collapse. And from that collapse, a solar system was born. As gravity pulled the gas and dust inward, the cloud began to spin, flattening into a vast disk. At the center, most of the matter collected, growing hotter and denser until nuclear fusion ignited. A new star blazed into life, the sun. Around it, the remaining gas and dust swirled, a chaotic disk where planets, moons, asteroids, and comets would soon emerge. This swirling disk, called the solar nebula, was a cosmic workshop. Within it, tiny grains of dust collided, stuck together, and grew. Over millions of years, these clumps formed larger and larger bodies, until some became planets, the architects of the worlds we know today. Closer to the newborn sun, where heat was intense, only rock and metal could survive. Here, the inner planets formed: Mercury, Venus, Earth, and Mars. Small, solid, and rocky, they were worlds built from the densest materials. Farther out, where it was cooler, gas and ice could condense. Here, the giants took shape: Jupiter and Saturn, enormous planets of hydrogen and helium. Beyond them, Uranus and Neptune formed, icy giants rich in frozen water, methane, and ammonia. Together, they sculpted the solar system, their gravity influencing the paths of countless smaller bodies. The early solar system was a violent place. Planets collided. Asteroids rained down in storms of fire. Moons were captured, broken apart, and reformed. It was during this turbulent time that our own planet, Earth, suffered a catastrophic impact with a Mars-sized body. From the debris of that collision, a companion was born: the Moon. The Moon has since watched over Earth for billions of years, stabilizing its tilt, shaping its tides, and becoming a silent witness to the unfolding drama of life. The chaos of the early solar system also delivered gifts. Asteroids and comets brought water and organic molecules to Earth, seeding the planet with the ingredients for life. What began as dust in a collapsing cloud of gas would one day breathe, think, and gaze back at the stars. The birth of the solar system was more than the making of planets and moons. It was the preparation of a stage upon which the drama of life, and eventually human consciousness, would be played. 4.5 billion years ago, Earth was a newborn world. Its surface boiled with volcanic fire. Asteroids and comets rained down from space. Lightning split the skies, while oceans began to collect across its surface. It was a hostile world, yet within this chaos, something extraordinary was stirring. The ingredients for life, water, carbon, hydrogen, nitrogen, and other elements, were present on Earth from the beginning. Some came from the planet's own rocks and atmosphere. Others arrived aboard comets and asteroids. In the shallow seas, under the warmth of the young sun, simple molecules combined into more complex forms. Amino acids, nucleotides, the building blocks of life. Through processes we are still unraveling, these molecules assembled into structures capable of storing information and replicating themselves. This was the spark of biology, the leap from chemistry to life. In the cradle of Earth's oceans, the first cells were born. For billions of years, Earth belonged to microbes. These tiny organisms transformed the planet in ways that would shape everything to come. Some learned to harness sunlight, inventing photosynthesis and releasing oxygen as waste. Over time, that oxygen accumulated in the atmosphere, turning Earth from a hostile world into one capable of supporting complex life. This event, known as the Great Oxidation, was one of the most important transformations in Earth's history. Without it, animals, plants, and humans would never have existed. Life did not remain single-celled forever. Around 600 million years ago, cells began working together, forming multicellular organisms. With cooperation came complexity. Creatures developed tissues, organs, and body plans. Evolution experimented endlessly, giving rise to an explosion of diversity. This Cambrian explosion filled Earth's oceans with strange and wondrous creatures, some fierce predators, others armored survivors. It was the dawn of animal life as we know it. 400 million years ago, plants and fungi colonized the land, followed by insects and amphibians. Life had escaped the seas and begun to shape Earth's surface. Forests rose, oxygen filled the skies, and ecosystems flourished. Then came the age of the giants. Dinosaurs dominated for over 150 million years, ruling both land and sky. Yet even their reign ended, wiped out by a cataclysm from space. A reminder that life, no matter how mighty, is fragile. From the ashes of the dinosaurs, mammals rose. Small, quick, and adaptable, they diversified into countless forms. Among them were primates, creatures with grasping hands, keen eyes, and growing intelligence. They would one day walk upright, use tools, and ask the question, where did we come from? From molecules to microbes, from dinosaurs to humans, the rise of life on Earth was a story billions of years in the making. A story rooted in the Big Bang itself, because without the stars, without the galaxies, without the forging of elements, there could never have been life at all. From the smallest cells came creatures of astonishing complexity. From primates came a species with language, imagination, and curiosity. A species that would not only survive, but learn to wonder about its own existence. That species was us. 2 million years ago, the first humans walked upright across Africa. They learned to make tools, harness fire, and share knowledge. Slowly, tribes grew into civilizations. Humanity spread across the globe, adapting to deserts, forests, mountains, and ice. Our ancestors built monuments to the heavens. They charted the stars, tracked the movements of the sun and moon, and told stories to explain their place in the cosmos. For them, the universe was a mystery filled with gods, spirits, and creation myths. But as centuries passed, human curiosity grew sharper. Philosophers asked whether Earth was truly the center of all things. Astronomers built instruments to measure the heavens. Galileo turned his telescope to the night sky and saw moons orbiting Jupiter, proof that not all things circled Earth. Isaac Newton revealed the laws of gravity, showing that the same force that pulls an apple to the ground guides the motion of planets and stars. The universe was not chaos, but order, governed by laws that could be understood. In the 20th century, humanity's view of the cosmos expanded beyond imagination. Edwin Hubble discovered that the Milky Way was not the entire universe, but just one galaxy among billions. He found that galaxies are racing apart, proof that the universe itself is expanding. His discovery gave birth to modern cosmology, and with it, the concept of the Big Bang. With telescopes on Earth and instruments in space, we now see nearly to the beginning of time. We can measure the faint afterglow of the Big Bang, trace the birth of galaxies, and watch stars die and be reborn. For the first time in history, the universe is revealing its secrets to us. Yet, for all our knowledge, we remain small. Earth is a fragile world orbiting an ordinary star in a quiet corner of a galaxy among hundreds of billions. Our entire history, all our struggles and triumphs, are but a flicker compared to cosmic time. And yet, from this small planet, we have reached outward. We have walked on the moon. We have sent probes beyond the edge of the solar system. We have left our fingerprints on the cosmos. In this way, we are both insignificant and extraordinary. To be human is to ask questions, to wonder where we came from, to seek our place in the vastness of space and time. And though we are newcomers on the cosmic stage, our story is inseparable from the story of the universe itself. Albert Einstein's theory of general relativity changed everything. It proposed that space and time are not separate entities, but are woven together into a single fabric, space-time. This fabric is not static, but dynamic, stretching and curving in response to mass and energy. A star bends the space around it. A planet like Earth orbits not because of an invisible force pulling it in, but because it is moving along the curved path created by the sun's mass. But if space-time can bend, could it also expand? That's the question scientists faced in the 20th century. Initially, Einstein himself believed the universe must be static. He even introduced a cosmological constant into his equations to prevent it from collapsing or expanding. Later, when evidence showed the universe was indeed expanding, Einstein called this addition his biggest blunder. In the 1920s, astronomer Edwin Hubble peered deep into the night sky with the most powerful telescope of his day. He discovered something astonishing. Distant galaxies weren't just far away. They were moving away from us. And the farther they were, the faster they receded. This wasn't just motion, it was expansion. The very fabric of space-time was stretching, carrying galaxies with it like raisins embedded in rising bread. This discovery shook science at its core. If the universe is expanding today, then in the past it must have been smaller, denser, hotter. Trace that logic back far enough, and everything we know converges on a single point: the origin of time and space itself. The moment we now call the Big Bang. Imagine playing the movie of the universe backward. Stars grow younger, galaxies shrink, clusters collapse inward. Atoms themselves unravel into a sea of subatomic particles. Keep rewinding, and even light struggles to escape the density of energy. Until finally, at the very first instant, 13.8 billion years ago, all the energy and matter of the cosmos are compressed into a singularity. A point so small, so dense that our current physics cannot fully describe it. But this singularity wasn't a dot sitting in empty space. It was the universe. Space, time, matter, and energy were born in that fiery instant. There was no before, no outside. The Big Bang wasn't an explosion in space. It was an explosion of space. And in less than a trillionth of a second, something extraordinary happened. The universe inflated. Not gradually, not slowly, but exponentially, faster than the speed of light itself. The theory of cosmic inflation, proposed in the 1980s by physicist Alan Guth, suggests that right after the Big Bang, the universe expanded at an unimaginable rate. In the blink of an eye, a space smaller than an atom grew to something far larger than our observable universe. Why does this matter? Because inflation solves some of the biggest puzzles in cosmology. For one, it explains why the universe looks so uniform on large scales, why distant regions separated by billions of light years have nearly the same temperature, as if they once were close enough to share the same cosmic conversation. Also explains why the universe appears flat, not curved like a sphere or saddle. It stretched space so vast and smooth that any curvature became negligible. In this sudden burst of creation, quantum fluctuations, tiny ripples of energy at the smallest scales, were magnified by inflation into the seeds of cosmic structure. These microscopic ripples eventually grew into the stars, galaxies, and clusters we see today. From randomness came order. From chaos, the blueprint of the universe.